Electrochemistry. This is our final unit that we'll be covering this year, and it's also known as redox chemistry or redox reactions. And it's one of my favorite units, so hopefully you guys will enjoy it as well. So the first bit that we're going to look at is, what does this whole redox thing mean? And the term actually comes from two terms. Redox is reduction and oxidation, kind of smooshed together. So a little history lesson here, looking at the origin of these words. So if we look first at the read part of redox, we're going into prehistoric times and looking at metallurgy. Most metals do not exist in their elemental form. There's a few exceptions that can be found in their elemental form, such as gold and silver. That's part of what has made them valuable. But most things only are able to be processed into metals by taking a large volume of ore and refining it, in which case we go from this big amount of stuff to this little bit of metal. And so we get this term reduction, right? We start out with a large amount, end up with a little bit. That's reduction. So some examples of things where this sort of thing happens, right? Iron being produced from iron oxide, tin being produced from tin oxide, copper being produced from copper sulfide. In each of these three reactions, you can see that there's another substance involved, right? They don't happen all on their own. And so when we have that sort of reaction, we say that this substance that allowed us to reduce the iron from the iron ore is called a reducing agent. So it's the thing that causes the other thing to be reduced. So for our examples here, our first one, carbon monoxide, is our reducing agent. Our second one, carbon's our reducing agent. And our third one, hydrogen, is our reducing agent. Picked those three examples quite deliberately because these are the three most common reducing agents used in actual metallurgy. So that was prehistory. We're going to go even more prehistoric on the oxidation side. We're going to go all the way to the technology of fire. So we've known about fire for a long time in terms of humanity, but it's relatively recent that we know about the role of oxygen in burning. And there's other similar reactions like corrosion. When iron rusts, for instance, it's another reaction that depends on oxygen. So once this realization of oxygen came out, taking a guess somewhere in the early 1800s, actually probably earlier than that. Anyway, once they figured out that there was this substance called oxygen, they were able to say, okay, we're going to call this group of reactions oxidation, where they involve these things reacting with oxygen. But there's other reactions that kind of would look just like a fire. They would be burning, but they involve other gases than oxygen, such as chlorine and bromine. So when you hear about chemical fires in some sort of industrial accidents, that sort of thing, they're often involving reactions with things other than oxygens, but very similar reactions. So that term oxidation, although initially really did mean reacting with oxygen, it got expanded to mean a wide range of these combustion and corrosion reactions. So if we look at those three examples, right, we have magnesium combining with oxygen to form magnesium oxide. That's a very typical combustion reaction, and one that we've done as an example in class, right, where we burned the little magnesium strips and we got the white magnesium powder. The aluminum plus chlorine, again, would be a very exothermic violent reaction. We would see that aluminum chloride being formed. I wouldn't want to be around that one because chlorine being a poisonous gas, not a great thing. But that is the reaction we would have. And copper reacting with bromine, similar sort of reaction, we get the copper bromide. Again, in all three of these reactions, just like in the three reduction examples, we have the thing that's being oxidized and the substance that's doing the oxidation. So the metal got oxidized and these other substances were the things causing the oxidation. So again, we call those oxidizing agents, just like the other ones were reducing agents. So for those three examples, oxygen, chlorine, and bromine were our oxidizing agents. Now something that happens in all of these 6 reactions, if you look at them, we have some kind of conversion from ions to atoms or vice versa, right? The 3 combustion reactions I gave, we started out with metals and nonmetals, and we ended up with ionic compounds. So on this side, they're just atoms on the reactant side. On the product side, they all end up being ionic compounds, so they went from atoms to ions. If we look at the other set of reactions, we had the reverse happening in many cases, right? Iron here started out as iron ions in the iron oxide, but ended up as iron atoms in the metal. Tin started out as tin 4 ions, ended up as tin metal. Copper started out as copper 2 ions, ended up as copper metal. And just a quick reminder, you can figure out the charge on those ions based on what they're combined with, because those charges have to balance. So this idea that we have these ions converted to atoms and vice versa happen in all these redox type reactions. Another type that is often easier to study in the lab is a single replacement reaction. So remember from the grade 11 level chemistry, a single replacement reaction, we have an element plus an ionic compound produces a different ionic compound and an element, so that one thing is replacing the other. In this case, the copper replaces the silver, right? It kicks the silver out, the copper ends up with the nitrate, and the silver ends up alone. If we look at that, and we look at the complete ionic equation, right, where all the ions are shown separately, right, because remember silver nitrate in solution is going to break up into silver ions and nitrate ions. Copper nitrate in solution is going to be copper ions and nitrate ions, copper 2 in this case. And so we can rewrite that equation with the same substances but written separately. And when we look at what's happening there, the copper is going from copper metal to copper ions. The silver is going the other way from silver ions to silver metal. So if we look at those two things separately, we see that the silver is like those reduction reactions, is starting out as an ion, ending up as a metal. The copper is more like those combustion reactions, is starting out as a metal, ending up as an ion. And that gives us our modern definition of oxidation and reduction. So reduction is defined as the gain of electrons, right? So the silver plus some electrons gave us silver ions plus electrons gave us silver. The copper is oxidation, and the reverse is happening. Electrons are being lost, right? They're being produced as part of our products. Now, we can't have one of these reactions without the other, right? Those two go hand in hand. The electrons are going somewhere. So when we say the electrons are lost, they're lost from the copper, but they go to the silver. So these are called half reactions because they're each only half of what's going on. So there's a couple little mnemonics that might help you remember which one's which. The one I tend to use a lot is Leo the lion goes grr, where Leo stands for loss of electrons is oxidation, grr stands for gain of electrons is reduction. Some people like a slightly shorter mnemonic, which is oil rig, which stands for the oil is oxidation is loss, and the rig is reduction is gain. Just have to remember we're talking about electrons in that mnemonic. We're going to come back to those again and again in the course of this unit. So, as I mentioned, copper is oxidized in that reaction, but it's also causing the silver to be reduced, so it's the reducing agent. Silver is reduced, but it's causing the copper to be oxidized, so it's reduced and the oxidizing agent. So the reducing agent is oxidized, and the oxidizing agent is reduced. Quick thing to distinguish between the processes, right? Oxidation and reduction are what's going on. And the substances, the oxidizing agent and the reducing agent, are the things that have what's going on.